Today, we're diving into one of the greatest scientific detective stories of all time, the hunt for what's actually inside the atom. And trust me, this is a story full of twists and shocking discoveries that didn't just rewrite textbooks, it completely changed how we see reality itself.
I mean, it's a pretty basic question, right? What are you made of? What is your chair made of? The air you're breathing? What is all this stuff really? For more than 2,000 years, pretty much everyone thought they knew the answer. Everything is made of these tiny little things called atoms. The word actually comes from the Greek atomos, which means uncuttable. This was it, the fundamental building block, the end of the line.
But, as the 19th century was wrapping up, a few scientists started getting this nagging feeling. What if the atom wasn't the end of the story? What if there was something even smaller hidden inside? And that one little question, well, that's what kicks off our entire investigation. So this is where our story really gets going. We're looking at the very first clues that started to hint that the atom wasn't just some solid little ball, but a whole complex world of its own.
So picture this. It's 1897, and a physicist named J.J. Thomson is messing around with what's called a cathode ray tube. It's basically a glass tube with almost all the air sucked out. When he zaps it with electricity, this mysterious glowing beam shoots across the tube. But here's where it gets really interesting. When Thomson brought a magnet or an electric field nearby, the beam bent towards the positive side.
That one simple observation led to some absolutely mind-blowing conclusions. First, since opposites attract, whatever was in that beam had to be negatively charged. Second, by measuring exactly how much the beam bent, he figured out that these particles were incredibly light, like 1,000 times lighter than the lightest known atom. And maybe the biggest shocker of all, it didn't matter what material he used to make the beam, he always got the exact same particles. They had to be a fundamental piece of everything. This mysterious particle was given a name, the electron. And just like that, for the first time in history, we had proof that something smaller than an atom existed. The indivisible atom had officially been broken open. But okay, just knowing the electron existed wasn't really enough. If you're a scientist, you want to know everything about it. They needed to measure its properties to really pin down what they were dealing with. And in 1909, a physicist named Robert Millikan did exactly that. In this absolutely brilliant experiment, he suspended tiny electrically charged oil drops in midair, perfectly balancing them between gravity and an electric field. By doing this, he was able to calculate the charge of a single electron, and he landed on this ridiculously small number. It was the fundamental unit of electric charge. A huge piece of the atomic puzzle was now locked in place. All right, so now we know atoms have these tiny negative electrons inside them, but atoms themselves are neutral. So that begs the question, where's all the positive charge hiding to balance things out? This puzzle led to two completely different ideas of what an atom might actually look like. So on one side, you had J.J. Thomson, the guy who discovered the electron. He came up with what's called the plum pudding model. Just imagine a blob of positively charged, pudding, with the negative electrons scattered through it like plums. Then, on the other side, you had a Japanese physicist named Hontaro Nagaoka who proposed a Saturn-like model, a big positive center with electrons orbiting around it like rings. Two totally different theories. How in the world do you prove which one is right? Well, you do it with an experiment. An experiment so clever and so profound that its results would send shockwaves through the entire scientific community. And the man behind it was a physicist from New Zealand named Ernest Rutherford. The setup itself was pure genius in its simplicity. Rutherford's team basically took a source that shoots out tiny, positively charged particles, called alpha particles, think of them as microscopic bullets, and fired them at a sheet of gold foil that was incredibly thin, only a few hundred atoms thick. And all around this setup, they placed a special screen that would light up with a tiny flash every time one of those particles hit. Now, if the plum pudding model was correct, with all that positive charge just spread out like a thin fog, then these alpha particle bullets should have just flown straight through the gold foil. I mean, maybe they'd get nudged a tiny bit, but that's it. And for the most part, that's exactly what they saw. Particle after particle zipped right through. But then, something happened that made no sense at all. About 1 in every 8,000 particles didn't go through. Instead, it was deflected at a massive angle. Some of them even bounced almost straight back at the source. Rutherford himself said it best. This was just unbelievable. The only way a fast-moving positive particle could bounce back like that is if it hit something incredibly small, incredibly dense, and also positively charged. The pudding model just couldn't explain it.
That single, shocking result completely destroyed the plum pudding model, and in its place, it gave us a brand new and much, much weirder picture of the atom.
From that one experiment, Rutherford figured out two revolutionary things. First, because most of the particles went straight through, the atom had to be almost entirely empty space. And second, all of the positive charge and nearly all of its mass had to be crammed into an impossibly tiny, dense center. He called it the nucleus.
A few years later, Rutherford would go on to identify the fundamental particle of positive charge inside that nucleus. He gave it a name, the proton. The second major piece of the atomic puzzle had been found.
But the detective story wasn't quite over yet. You see, there were still a couple of nagging mysteries. For one, the protons in the nucleus only accounted for about half of its mass. So where was the other half? And at the same time, chemists were finding that atoms of the same element could sometimes have different masses. How was that possible?
The final pieces of this massive puzzle clicked into place over the next 10 years or so. First, a chemist named Frederick Soddy proposed the idea of isotopes, basically atoms that have the same number of protons but different masses. That explained the second mystery. Then, in 1932, James Chadwick finally found the source of that missing mass, a particle in the nucleus with no charge at all, which he called the neutron. It added mass but didn't change the element. And that was it. Case closed.
So let's just quickly recap this amazing 35-year journey. It started with Thomson finding the electron, then Millikan measured it, Rutherford used it to find the atom's tiny nucleus, Soddy figured out the isotope puzzle, and finally, Chadwick delivered the last piece, the neutron. Our modern view of the atom was complete.
Think about it. In just a few decades, science went from an indivisible, solid ball to this incredible miniature solar system of protons, neutrons, and electrons. They had solved one of the oldest mysteries in science. But in cracking open the atom, they had also unlocked the door to a new, far more powerful, and frankly, more dangerous mystery, the immense energy hidden inside the nucleus itself. But that's a story for another time.